Okay, section 2.1, transport across the cell membrane. Polar molecules and ions have difficulty crossing phospholipid bilayers. Ions cannot cross a phospholipid bilayer, whereas small polar molecules will have extreme difficulty. Small nonpolar molecules can easily diffuse across phospholipid bilayers. So for the example of small nonpolar molecules, we have O2, CO2, N2, and steroid hormones, but the small nonpolar are these. These can easily diffuse across a phospholipid bilayer. And I guess before moving on, we should note that diffusion is literally dependent on that molecule or that ion, meaning that each ion and each molecule only sees its own gradient. So for example, O2 will see its own gradient and it will move down its gradient across a phospholipid bilayer, and it can cross a phospholipid bilayer very easily. CO2 sees its own gradient and will move down its gradient through the phospholipid bilayer, and it can cross the phospholipid bilayer very easily. Steroid hormones are a little bit bigger, actually a lot bigger, but they're still hydrophobic, but they're not so big that they cannot cross. So steroid hormones have relative ease crossing a phospholipid bilayer. Now, small uncharged polar molecules, what we mean by uncharged are that they don't have a full negative or positive charge on them. So these are polar molecules or partial charges on them. They're very hydrophilic. They will have more difficulty crossing a phospholipid bilayer, as being shown here in this arrow. Now, large uncharged polar molecules, such as glucose and sucrose and etc., these are much larger than H2O, urea, glycerol, or NH3, ammonia, and they will have much more difficulty getting across a phospholipid bilayer than the other molecules mentioned before. Ions that are being shown here, sodium, potassium, calcium, Cl-, magnesium, H+, etc., they will have almost no ability to cross a phospholipid bilayer, no matter which direction their gradient or how strong their gradient is. So the most important thing about the statements that we just made, that we're talking about a phospholipid bilayer, and that's what's being said here. The above is true for a phospholipid bilayer and not a cell membrane. A cell membrane will have transporters and channels that will allow ions and small polar molecules to cross it easily, but under cellular control. So, for example, we know that glucose can cross the cell membrane through the glucose transporters. That was an example that we saw in section 1. And then we're going to get to other examples where ions and ion channels, ions can easily cross the cell membrane when these ion channels are open and move down their gradient. The cell membrane is permeable or can be made permeable to ions and small polar molecules. This is accomplished through the actions of the following membrane proteins. We have transporters, membrane proteins with binding pockets for the solute. It moves across the cell membrane. The binding pocket is either exposed to the extracellular environment or to the cytosol, but not both. Transporters can facilitate active or passive transport, meaning moving molecules against their gradient or with their gradient. So here's an example of a transporter being shown here in this picture. And you can see that the binding pocket right here for the ligand, it's either exposed to one side or the other, but not to both at the same time. And that's what that statement means. Now, channels, membrane proteins that create a pore in the membrane. These proteins do not bind a solute, but they are still specific for what they conduct across a biological membrane. Channels can only facilitate diffusion, meaning that they cannot facilitate active transport. So we have an example of a channel protein here, and you can see it just creates a pore, an opening, for which it will specifically allow a certain ion to get across, if we're talking about ion channels. So it'll be specific for the molecule or ion that it will allow to cross, and it will not allow other things to cross through that pore. Some mammalian cells, such as nerve and kidney cells, devote up to 2/3 of their total metabolic energy consumption to such transport processes. So 2/3 of the ATP that is being made. Diffusion and the electrochemical gradient. Animal cell membranes have a voltage or potential across them. The inside of the membrane is slightly more negative than the extracellular side, or put differently, the extracellular side of the membrane is slightly more positive than the cytosolic side. This leads to a resting potential that is negative, ranging roughly from -50 millivolts to -100 millivolts, depending on the animal and cell type. Here's my cell membrane, and I'm just showing the phospholipids, not the proteins and etc. And what you'll have is slightly positive on the extracellular side and slightly negative on the intracellular or cytosolic side. Now, before we carry on, maybe it's important to define what the cytosol is. The cytosol is everything between the cell membrane and the nuclear membrane that is outside of organelles. So, to define this, the solution between cell membrane and nuclear membrane and outside of organelles. Typically, when you see a picture of a cell, a cartoon drawing, all that empty space that is outside of the organelles but still within the cell. I mean, technically, you can say any space within the cell that is outside of the organelles because the nucleus is an organelle, right? But we just want to define a little bit better. Okay, so the membrane is slightly more positive on the extracellular side and slightly negative on the cytosolic side. Okay, and I've drawn this in a way that it's showing an extreme difference between the charge, but it's not that extreme. But still, even a little bit of difference in charge distribution, where you're a little bit negative on the cytosolic side and a little bit more positive on the extracellular side, will create a voltage ranging from -50 millivolts to -100 millivolts. It just depends on how large that difference is. Now we're going to define the electrochemical gradient. If a molecule does not have a net full charge on it, then it will attempt to diffuse down its chemical gradient, aka concentration gradient. So this is probably something that you have seen and learned from 140, and that is that molecules will move down their concentration gradients or chemical gradients. And that is that they'll go from an area at a higher concentration to low concentration. If a molecule has a net full charge, and this is important, net full charge, not partial, or it's an ion. Ions have a net full charge, like sodium has a full positive charge, Cl minus, full minus charge. It will move down its electrochemical gradient. The electrochemical gradient is a combination of the force acting on the charged molecule, or ion, due to its chemical gradient, meaning the concentration difference between one side and the other, and the force acting on it due to the potential on the membrane. A positively charged ion, such as sodium, will have a potential gradient, the electro part of the electrochemical gradient, pointing towards the negative side of the membrane, while a negatively charged ion such as Cl- will have a potential gradient pointing towards the positive side of the membrane. So let's draw this out. And the typical way I like to draw this out so I don't have to draw phospholipid bilayers is here's my line, and this line is the cell membrane. Okay, and this is the extracellular side, and this is the intracellular or cytosol. Okay, so extracellular, intracellular. And we know that we're negatively charged in the interior side, then positively charged on the exterior side in a resting cell, in a resting membrane. Okay? Now, if I have sodium on both sides, but the concentration of sodium is much higher on the outside compared to the inside, what I will have is a chemical gradient. So red is for chemical gradient, and that is the same as the concentration gradient pointing in, right? Because I have a higher concentration of sodium on the outside, And I also will have a potential gradient pointing into the cell because positive wants to go to negative, right? So this is the potential gradient. So potential is in green. Now for Cl-, if I had the same thing, Cl- on the outside, Cl- in the inside, and I have a higher concentration of Cl- outside, then the chemical gradient for Cl- is pointing in, but Cl- is negatively charged, so the potential gradient is pointing in the other direction. It would want to stay on the positive side, so they counteract each other in this case. Thus, a molecule or ion in solution will move down its electrochemical gradient until it reaches equilibrium. So, if you have a positive or negative charge on that ion or molecule, it has both the concentration or chemical gradient and it has the potential gradient. Those two things, when you add them up, it's either pointing in one direction into the cell or the other direction out of the cell, right? Now, if you don't have a charge, the molecule just doesn't have a full charge on it, then the only thing that you have to worry about is the chemical gradient. So if I go back to that picture that I had above, if I have glucose, for example, and I have a higher concentration of glucose outside, well, glucose only has a chemical gradient, so its gradient will be pointing into the cell. So you might have noticed that in the beginning, I try to be careful of not saying concentration gradient, because we're getting to this point where we're talking about electrochemical gradient, and that is more important, especially for the topics we'll be discussing in section 2. So in the case of glucose, it technically has an electrochemical gradient. It's just that the electro part is missing because it doesn't have a full charge on it. Whereas for sodium and Cl-, well, they have a full charge on them, so they have their chemical gradient, and now they have their potential gradient too, that affects which direction its full gradient is pointing in, because the full gradient is adding the chemical and the potential gradient together and seeing which direction the gradient is pointing. Thus, a molecule or ion in solution will move down its electrochemical gradient until it reaches equilibrium. For a molecule that does not carry a net full charge, equilibrium is reached when concentration across the membrane are the same. So, for example, for glucose above, equilibrium is reached when you have equal concentration of glucose on both sides of the membrane. For an ion or a molecule with a full net charge, equilibrium is reached when the force acting on it by the chemical concentration gradient equals the force acting on it by the potential gradient. So those two things have to equal each other. So this picture right here is just showing you how this works. So here we have a membrane that doesn't have a potential on it. So the only thing acting on this positive and negative charges is their concentration gradient, and they have a higher gradient outside than inside, so the gradient is pointing directly in. But if you put that potential on the membrane here, where you're positively charged outside and negatively charged inside, for the positively charged molecule, now its concentration gradient and potential gradient are pointing in, so its electrochemical gradient is pointing in strongly, and you have this big fat arrow kind of showing that it's pointing in very strongly. For the negative molecule, the molecule that has a full negative charge, here you can see that, well, its concentration gradient is, or chemical gradient is pointing strongly in, but since it's negatively charged, it wants to stay on the positive side, so its potential gradient is counteracting the chemical gradient, and the arrow is much thinner, meaning that its electrochemical gradient overall is not pointing in very much. Okay, so of course we can put some delta G's to this, and the delta G of these equations are very similar to what we've seen before, especially for concentration. So the delta G for concentration is being shown here, and the delta G for the potential gradient is being shown here, where V is membrane potential, C O and Ci are the outside and inside concentrations of ions respectively, or molecules. R is the gas constant. T is the absolute temperature in Kelvin. F is Faraday's constant. Z is the valence of the ion. The valence of the ion right here, it just means that what is the charge. So if calcium has a 2+ charge, so its valence would be 2. The Z number would be 2. Sodium has a single plus charge, so the Z number will be 1. Cl- has a -1, so the Z number will be a -1. Okay, so of course we can go ahead and simplify these equations because we're kind of working in an environment that does not change that much. The temperature is not going to change, and etc. So when we do that, our delta G of concentration will equal to -5.9 log of CO over Ci, concentration outside over concentration inside. Delta G volt will equal to 0.096 Z, the charge, times V, and the voltage will be in millivolts. For a molecule which does not carry a net full charge, Z will equal to 0. So for like glucose, H2O, those type of molecules where they're polar, but they don't have a full net charge, Z becomes 0. So if Z becomes 0, I stick in 0 here, the delta G of the potential gradient disappears, right? Poof, it's gone. Now, if the concentration outside equals to the concentration inside, right here, then this thing becomes 1, and log of 1 is 0, and this thing disappears, right? So the delta G of concentration will equal to 0 if you have equal amounts on both sides, because it'll be a log of 1 will be 0, right? All right. So if an ion is at equilibrium across the membrane, so now we're dealing with an ion, because an ion has a charge, then you have a delta G volt and you have a delta G concentration. Then delta G volt plus delta G concentration equals to 0. When you add both of them up, you're at equilibrium because that's the total delta G of the electrochemical gradient. Total delta G will equal to delta G volt plus delta G concentration. So if I put these numbers in, or the equations in from above for delta G volt and delta G concentration, this is the equation that I get. If the voltage across the membrane is known, the relative ratio of concentrations needed across the membrane to reach equilibrium can be calculated. So for example, if I know the voltage on the membrane is -50 millivolts, well, I stick -50 into V, and of course, I'm talking about the electrochemical gradient for a certain ion, and I want to see what concentration ratios I need across the membrane. Then I will know the Z number too, because if it's sodium, it would be a +1 for Z. Cl- it will be a -1, etc. And then I can solve for this, and I know at this ratio of concentrations across the membrane, that ion will be at equilibrium, meaning that even if I open up channels, nothing will move across. The net movement of ion will be 0. Okay, net movement. Okay, so we have a couple of examples that we can work through here. And the first one is, assume the membrane potential is -90 millivolts. So right off the bat, V equals to -90 millivolts. And that the Ci of potassium is 140 millimolarity. So Ci is 140 millimolarity. And since we're dealing with potassium, we know Z equals to +1. Okay? What is C0? Or CO, I'm sorry. So what is CO? That's what we don't know. So let's take our equation from above. So now we're going to plug in our numbers, and we have 0.096. Z is 1, so that disappears. V is -90 millivolts. And you don't need to put the units for millivolts in here because the 0.096 has millivolts in it, and they will cancel out. And both of this side and this side also have kilojoules per mole. So -5.9 log of, and C0 we don't know, but Ci is 140 millimolarity equals to 0. And that will give me -8.64 equals to, and I'm going to move the 5.9 to the other side. Just to make my life easier. So this would be 5.9 log of C0 over 140 millimolarity. Then I'm going to divide both sides by 5.9, so I have negative 8.64 divided by 5.9 equals to log of C0, or CO, I'm sorry, I keep saying C0, it's CO over 140 millimolarity. And that would be 1.46, or negative 1.46, equals to log of CO over 140 millimolarity. Come here. And I put both sides to the base of 10. 10 to the negative 1.46 equals to CO over 140 millimolarity. And that is 0.035, about there. 0.035. So multiply, so C0 equals to, or CO equals to 4.85 millimolarity. Okay. So as impossible as this seems on first glance, that I could have, and this is again intracellular and extracellular, and I have positively charged, negatively charged, where I have a membrane potential of minus 90 millivolts, that potassium will be at equilibrium if I have 140 millimolarity here and 4.85 millimolarity here. So in this case, you can see that, okay, the concentration gradient, which is in red, is pointing directly out, but the potential gradient, which is in green, is pointing directly in, and they're the same amount. So these two arrows are equal to each other, so when I add them up, I get 0. They cancel each other out. Okay? Example 2. Assume the membrane potential is minus 90 millivolts, so membrane potential is minus 90 millivolts, and that C0 and Ci of sodium are 145 millimolarity and 10 millimolarity. So we have, and this is sodium now, so CO equals to 145 millimolarity, and Ci, did I say C0 again? CO is 10 millimolarity. What is sodium's equilibrium potential at these concentrations? Okay, so although this is giving you a V, right? It's essentially telling you that a cell at rest will have a V of minus 90 millivolts. Let's just assume that our resting cell, has a minus 90 millivolt potential across it, and that the concentrations of sodium are this, okay? What it's asking you is saying, what is the actual equilibrium potential for sodium? We don't know that, okay? Because at these concentrations and this potential, sodium is not at equilibrium unless we solve for V and we get minus 90 millivolts. So what we're going to do is we're going to solve for V. So let's put our equation down again. So 0.096 ZV minus 5.9 log of CO over Ci. Let me just, and that's equals to 0. Let me double check that because I don't want to make a mistake here. Yep. Okay, we're good. And we're going to solve for V. So Z we know is +1, so that kind of leaves us away. That goes away. We have V, 5.9 log of, and CO is 145. I'm not going to put in the units because these are both in millimolarity, so they cancel each other out. And what I have is 0.096 V. And actually, I'm going to pull this whole thing to the other side. So I have 5.9 times log of, and this is going to be 14.5, right? So this would be 5.9 times 1.16, and I'm dividing both sides by 0.096, and that will be my V. So V equals to, so it'll be 71.3, about there, close enough, millivolts. So you can see that at these concentrations of sodium, that at minus 90 millivolts, sodium is very far away from the potential that it needs to be at equilibrium. Now, there's a reason why this question is written this way, and we're going to get to it shortly, actually very soon, is that this is actually true. Both for potassium and sodium, those concentrations that I put up there are actually the concentrations of potassium and sodium across the cell membrane, and they're maintained at those concentrations. Those concentrations don't change. If those concentrations change dramatically, the organism will die. Okay? And this is extra. Just let's label this before we go on. Intra. So let's have sodium in blue. For sodium, you have 145 millimolarities out and 5 to 10 millimolarities in. And for potassium, it's almost the opposite. So potassium will have in green, you have about 5 millimolarities outside and about 140 millimolarities inside. Okay? And remembering the potential on the membrane where it's negative, the resting membrane, which is slightly negative in, slightly positive out, giving it a negative voltage. Well, we already established that potassium, its concentration gradient is pointing out, so concentration gradient in red, and its potential gradient in purple is pointing in, because positive wants to be on the negative side, right? Now for sodium, the chemical gradient is pointing out, but so is the potential gradient when it's at like minus 90 millivolts. So sodium's electrochemical gradient is pointing strongly into the cell, while potassium's, kind of pointing out of the cell a little bit, not much. Or if it's at minus 90, it will be at equilibrium. Just showing you that for sodium to get to equilibrium at these concentrations, the potential on the membrane has to switch completely. So let me go ahead and actually take away these arrows real quick. And what I'm going to do is I'm going to turn the membrane potential positive, okay? So now my membrane will be negative on the outside, and positive in the inside, where it looks like something like the V equals to 71.3, for example, okay? It's a positive voltage. Now, when you have this, well, sodium's concentration gradient or chemical gradient in red is still pointing in, but its potential gradient is pointing in the other direction. But what will happen for potassium? Well, potassium's chemical gradient is pointing out, and now its potential gradient is pointing out, right? You have to remember one thing when we go through this section. And this is going to be a thing that is going to throw people off. And if some of you have taken 140 with me, and when we covered diffusion, I always said, don't tell me when the system is reaching equilibrium. Just tell me if I put the system in this way, which direction will things move? And the reason for that is, in a living organism, the concentrations of sodium, potassium, Cl minus, and calcium, and these other ions, they don't change. They're going to be maintained. What's going to change is the potential on the membrane. Okay, so I think this is about as much as I want to cover in this video. Yes. Okay. And we will continue later. Thank you, guys.